I moved. I changed the title of my talk because I thought this topic would fit slightly better with the overall topic of the workshop. And so what we have been trying to do. So it's a work I've done in Berkeley during my postdoc last year. And so what we have been trying to do is to use a machine learning tool, and specifically a recurrent neural network, in order to predict, to follow the state of a quantum system, so quantum trajectories along a stochastic evolution, but only using raw observations. So can we estimate the state of the system just in a model-independent way using this a powerful tool of machine learning? And so the question we were asking is that, like, in most of the quantum experiments are like very typical and look something like this. So you have like a preparation at the beginning. So if you have a qubit, your preparation can start with a measurement, right? So you have like a binary outcome of this measurement, that you can herald. Then you perform a preparation. Then you have like the proper quantum evolution of your experiment. And at the end, you have like a kind of symmetric operation compared to the beginning. So you have like a tomographic pulse and a measurement that gives you a binary outcome. Okay, and so this is pretty general, like for superconducting circuits, ion trapped or quantum optics. Okay, and so in a way, you can kind of abstract it in completely, right? So where you have like just a black box where you input like a bit, input bit x. You choose a measurement setting with knobs, so you just press knobs. You have like this complicated evolution or not, right? And the measurement is similar, so you choose a measurement knob that you press, and the measurement gives you an output bit, +1 or -1 in the case of a qubit. Okay, and so the goal of quantum mechanics is to be able to predict the most likely outcome y, given your preparation setting and the bits that you have inputted, right? And so if you want to do that, you usually have a state in a Hilbert space. You apply unitary operators to it and an Hamiltonian evolution, right? And you use the Born rule in order to extract this probability distribution, right? So that's for the ideal case, but now if you want to deal with a statistical mixture in your system, so you're using like the density matrix formalism, right? And so with the trace, and you know that very well. Now, if you want to deal with decoherence, for instance, then you need to move your Hamiltonian evolution into a completely positive trace-preserving map. Okay, and so like for an experimentalist, this can be like a little tough to handle. So we try to So the goal is to see if there is a way around using all this formalism and to do it in a more like a model-independent way. And so, for instance, in our experiment, we can also like monitor the noise produced by this box, right? So we just place a microphone or an amplifier, okay, and we get like this continuous measurement trace that Antoine talked about before. And so now, if you want to get the most likely outcome out of this box, right? So you need to have like a pretty talented student that is going to calculate all the positive operator value and measure that correspond to the exact noise trace you got. And then you will be able to tell the most likely outcome of this experiment. Okay? So one problem for an experimentalist is that you need to calibrate all the physical parameters that goes in these operators in an independent way. And even if when they are calibrated, it's better to fine-tune them, as Antoine described before, in order to make this evolution work in practice. Okay, but there is something interesting that, like, this kind of probability distribution, right? It's exactly what machine learning is very good at dealing with. Okay, but so you can fit sort of fit this probability distribution with like many inputs, as many inputs as you want, if you have like a large enough set of instances, okay? And so this supervised deep learning is going to be able to infer this probability distribution, and no matter how complicated is the problem, so you can recast language translation or image and speech recognition in this form. So that's the most generic form for supervised deep learning. Yeah. And so in our system, we are dealing with superconducting circuits. And so we have like a very large set of data. So we can produce like 1 million traces of this type per minute. Okay. So, so the large amount of data is not the problem. It's not a problem at all for us. And so we'd like to infer this without any prior on quantum mechanics. And something nice is that, like, in the end, if you have like enough knobs on the tomography side, and so if B span a complete set of observables, then knowing this probability distribution is equivalent to know the state of your system. Okay, and so this is what we are going to do. So this is my outline. So first I introduce like a superconducting qubits, and so it's in a simple case, so 1 qubit and 1 continuous measurement. Then I will show like a few examples of quantum trajectories solved using the master equation, and then I would show how neural nets can be used to infer those trajectories. So superconducting circuits, we are working so in the circuit realm, which is around the microwave frequencies. Okay. And so to do quantum mechanics at such a low energy, right, you need to cool down your system to cryogenic temperature. So the quantum domain is around here. So you need to go to, like, let's say 10 millikelvin. Okay, and like fortunately at this temperature you have like superconductors that you can use for free. Okay, so you have like a very nice overlap right here. And so using the superconductors, you can make electrical circuits, such as like this LC oscillator. And thanks to their like non-dissipative character, you can just forget about the resistance. Okay. So this LC circuits, so you have like a 2 variable, which is the flux threading the inductance and the charge on the capacitor plate. Okay. And fortunately, those 2 variables are conjugated variable. So they commute and give IH bar, so which is reminiscent of the position and the momentum of a particle in a well. And so immediately you can see that this Hamiltonian corresponding to this oscillator gives you like this very nice harmonic oscillator. Okay, so now the key element of those Josephson circuits are the Josephson Junction, is the Josephson Junction. So you can think about the Josephson Junction in terms of dissipationless nonlinear inductor. Okay, so it's made of an insulating barrier that is separating like 2 superconducting leads, and so the Cooper pair tunneling through the barrier is going to give this nonlinear inductance character. And so now what you want to do is you take your LC oscillator and you just replace the inductor by this Josephson junction. And so as a result, what you get is this cosinusoidal potential instead of the harmonic potential. And what you see that like you lift the degeneracy of your transition, and now you can address like the 0-1 transition specifically. Okay, and so you can isolate the 0-1 transition, and this is what you call a qubit. Okay, so this is our qubit. So there are many types of qubits, variation on the harmonic oscillator, and so you have like a proper periodic table for qubits, where like you have like on one axis the number of shunting junction, and on the other axis the shunting capacitance. And so what we typically use is this transmon right here. So now you want to couple your spin, okay, your qubit, to some light field to do some circuit quantum electrodynamics. Okay, and a simple way to do it is just a capacitive coupling. Okay, and so you get like this extra term that is going to couple this potential to this potential. Okay, so that's our experimental system. So in this experiment, we are using this 3D bulk waveguide cavity with the microwave field here is highlighted in blue. Okay, so that's the light part. And here we place a transmon qubit on a sapphire chip inside the cavity. Okay, and the transport qubit is this two pads of superconductor shorted by a Josephson junction. And so that's our system with the typical strengths we get. So now we move to the dispersive coupling, so where like the two oscillators are far detuned, and so the resulting coupling is of this form. So where the spin you get like sigma z a dagger a. So what it means that like when the spin is up, so depending on the spin state, okay, you shift the resonance frequency of your harmonic oscillator, okay. And so this is actually very convenient for probing the state of the qubit, okay? Because now if you shine some light, some microwave light on the cavity, okay, if you look at the reflected phase of this of the light, the phase of the reflected light, you can get like two values. So the up value will tell you that the qubit is in up, and the down value tells you that the qubit is in down, okay? And so this is the way we are measuring our system. Now, this signal is typically very weak, only a few photons, and at the microwave frequency, it's a very weak signal. So in order to be able to resolve those fluctuations, those quantum fluctuations associated with the signal, we need like a very powerful amplifier. And so we are making our own parametric amplifier, which are like named like Josephson amplifier. So in our case at Berkeley, the amplifier looks like that, and it's made. There is a squid, which is the key part of the circuit once again. And so here we can perform a homodyne detection of the input signal. Okay, so that's for the experimental part. And now what we want to do is to perform a weak measurement of our qubit. So what we do is instead of sending this large input field, we send just a very, very little signal such that the output signal is not completely resolved. Okay, and so in this case, we just acquire just a little bit of information about the state of the qubit. So this is called a weak measurement. So we are unable to resolve the state of the qubit for fundamental reasons. Okay, and so yeah, you get partial information. And now if you average longer, then your Gaussian distribution are going to get separated. And so that's the case where you move to a strong measurement. But this has been like very well described by Antoine in the previous talk. So now trajectory. So you can think about trajectory as like some sort of Bayesian inference. So let's say you get like a homodine voltage on the very far left right here. And so if you get like this voltage value, you are way more likely to be in 1 than to be in 0. And so this is very informative. Like it's similar on the right. However, if you are in the middle, it's much harder to tell what is going to happen. Okay, and so that's the weak measurement. But you can still do something by using this POVM measurement. And so in the blue and red case, you have like projected basically your qubit. But in the intermediate case, you can still extract a little bit of information out of this signal. And this corresponds to the measurement back action on the qubit. So if you want to do it like very precisely, you need to compute the state of the system after its interaction with the ancilla, as Antoine described. Okay, and so here our experimental data. So we have like one trace. So I don't know, it's one of the two traces, which correspond to the measurement record, and that's a movie of the evolution of the qubit along one of these traces. Okay, and so you see like you can have like a fluctuation at the beginning, and after a while you just project the state of your qubit. Okay, so that's this is what we call a quantum trajectory. Now you can do like a slightly more. You can go to like a slightly more complicated experiment where instead of having one measurement channel, you have like two measurement channels, and you can engineer your system such that the measurement channel are not measuring the same operator. So for instance, this one is going to measure a sigma z operator, and this one is going to measure the sigma x operator, and you can perform a weak measurement simultaneously on those two operators, and try to infer what will be the state the trajectory of the qubit in those two cases. And so you can actually tune the axis of those measurements at will. So in the first case, this is where like the two measurements are commuting observable. And so what you see is like very similar to a projective measurement. So you have like first a trajectory, and then the two instances here are collapsing on the two different poles. Okay. But now if you choose two measurement axes that don't commute, right? This is typically what you get. So instead of staying in the plane, you have like a diffusive behavior on the equator. Okay, and so you will keep this persistent diffusion inside the Bloch sphere. Okay, in this case, because the back action are like are not along the same axis. It's not along the same axis. There is no pointer state anymore. Then you can do like some analysis of the statistics of the trajectory depending on the measurement rate, right? And you see like you have a projection on the poles if the two measurements are aligned, and you get like a persistent diffusion, homogeneous persistent diffusion if the two axes are maximally non-commuting. Yeah.
Sorry, why were the two different arrows?
Hmm?
The previous thing, you had a red arrow and a blue arrow. For the plots.
So for which one?
Yeah, why are the two of them?
Oh yeah, so just two instances of the trajectory. I just showed two different trajectories. Like, so
It's not just that you're only including one channel.
No. No, sorry. It's two instances, just to show two instances. Okay. But like, you know, we have like millions of those trajectories available. It's like just chosen randomly. So yeah, two instances, you know, just to show like various, a few behavior. Okay. So now we can also take a step back, right? And now we just have like one measurement channel, and so this is the case we are going to be interested in for the case of the neural networks. So in this case, you have one qubit, okay, but you apply a Rabi drive along the sigma x-axis in the same time as the measurement, okay? So now you have like a non-QND measurement because the Hamiltonian is not commuting with the measurement operator anymore, okay? So things are slightly more complicated, but you can use like the master equation in order to model it. And so that's the result of a quantum trajectory. So starting from the sigma x here, and so you see that you have like a competition between the Hamiltonian evolution, so the Rabi drive in this plane, and the measurement that is adding some noise, some back action on top of it. Okay. And so that's a typical trajectory we can extract. However, just like Antoine mentioned it, so to extract this trajectory, you have like a few hypotheses to do. Like for instance, you have to make sure that the noise is it's a Markovian noise, right? So a white noise. There is no correlation. But if you have, as mentioned, so if your amplifier have a lower bandwidth, you know, like this master equation is not valid anymore, and so it can get a little tricky. So the question we ask is, can we use a neural network, machine learning, in order to infer this kind of trajectory, but without any prior on the model, no prior on quantum mechanics, and only using raw data. Okay, so what kind of data do we have? So as I mentioned at the beginning, so we have like an input bit at the beginning that corresponds to the heralding measurement. Okay, we have like this, so that's the input bit. We have like a stochastic signal. It's a very noisy trace, and we have like the tomographic measurement at the end that gives us also a bit. Okay, and so using that, we are going to try to infer the quantum trajectory of the system. So this is typically, so what we want to do is just to send directly the signal to the computer, right? And we want the computer to be able to interpret the signal on the fly, to be trained on the signal on the fly. Okay, so let's have a little break on the experimental system. And so let's try to see how a neural network works. So that's a single artificial neuron. So it's built. So it's named like this because it's reminiscent to it's a neuromorphic gate. Okay. So you have like inputs x0, x1, x2. You have weights that are connecting the inputs to the actual neuron. Okay. And so what is going to happen is like if the neuron has this like nonlinear activation function, okay, and so if the signal at the input of the neuron gets large enough, the neuron is going to fire its signal, right? So which is represented here by 1, okay, and so the weight matrix can be adjusted, and you have so the moment at which the neuron is going to fire is given by this bias term associated with the neuron. Okay, so in this case, we get like this very simple sigmoid function at the output. So that's so in practice, actually, most of the people are using this this kind of activation function because they are easier to compute. So just to rectify linear unit, but as soon as it's nonlinear, it's enough. Okay, so let's look at a simple artificial neural network. So it's a 2-layer network. Okay, so you have like one input here connecting to a first layer. So the first with the weights given here. Okay, so this is the activation function of the first layer as a function of x. Okay, and now I recombine the output of the 2 layers of the first layer to the second layer, and you can see that I can generate like this this kind of function. Okay, and so here I've chosen the parameter at random. But by adjusting the parameter, basically, you can see that you could fit like some Gaussian distribution, right? Avec like slightly asymmetric Gaussian distribution. Okay, so this is the kind of stuff like a very simple artificial network would be able to do. But so now we want to move to a deep neural network. So meaning that you have like several layers of neuron stack on top of each other. Okay, and now the kind of function you can generate out of this neural network is much wider, and it lives in a much larger dimensional space that is given by the number of inputs. Okay, and so now you can see that. So one way to represent the state of one layer is to encode it on a vector. So H encodes the state of the output of one layer as a vector here, and so you can compute this output just by applying the sigmoid activation function, which is function of and this vector of biases. Okay, so in the end, you can see that neural networks is all about like a linear algebra with like a nonlinear function inserted between those matrix multiplications. Okay, and so something quite crucial to understand about neural network is neural networks are actually like differentiable computers. Okay. So as opposed to a normal gate, right? Here you can differentiate the output of one layer with respect to its input. Okay, and so that's a crucial properties for optimization because what you want to do then on those weight matrices is to be able to do some gradient descent. Okay, so this property is a key property of this neural network. Okay, so now you have to define a loss function. Okay, so you get some output out of your neuron, and you want to compare the prediction of the network with, for instance, here the tomography bit we get out of the experiment. Okay, so here we are just using a cross entropy loss function. Okay, and so this loss function defines a landscape that we would like to minimize. So now that's the key point. So we want to perform some gradient descent. So we want to update the weight matrix in order to go down in this potential. And so what we need to do is to compute a linear function placed in between. Okay, so it's most of a neural network is matrix multiplication. Okay, and so what you want to do then, so you have your input, you compute your output, you compare it to the with the function with the actual experimental result, and you optimize your weights. Okay, and so you have like a flow like this. That can so that's the flow for training. So you see that we don't really want to use like this kind of network because you see all your input states are are placed like so there is no hierarchy at all on the form of the input, right? And so basically you would just get the final result of your the final bit after the full trace, okay? But you would like to decompose this prediction in smaller steps, right? And so we are not going to use this crude architecture, but like instead a more refined one. So you have like two refined neural network architecture. So the first one is a convolutional neural network that are very well suited for spatially ordered data. So you will typically use this in order to do some image recognition. Okay. So where you have like the neural network is decomposed between nearest neighbor, basically, on a picture. And so the one we are going to use is the recurrent neural network, which is way more suited for time series. So where you have like some causal signal. Okay. And you are inputting your signal step by step. So here, like for translation, right? So you input the input sentence. So it's not it's like a bot. So you just input like the data word by word. Okay. So that's a recurrent neural network. So you are only using one weight matrix. Okay. And you loop the output of this layer to its own input. Okay. But the only difference is that here you are going to input your data one by one. Okay. So I'm going to input my voltages one by one in the network. Okay. And so at each time step, I will also get a prediction. Okay. So it's more suited for this kind of trajectory purpose. And so, like similarly, you will compare your output with the data, with the tomography, through a loss function, and you will optimize this weight matrix. Okay. So I think there is like that's a very good example of on what is capable, what a recurrent neural network is capable of. So here, so it's an example out of this paper by Carparty et al. And so what we are going to, what they try to do is to do some character level language modeling. So meaning that you feed it the full book of War and Peace, the 3 tomes, and so you are going to train the network in order to predict what is going to be the next character. Okay, so you input the current letter, okay, and the output will be like the most probable next letter, okay. And so, like for instance, here we inputted like step by step all this text, right? And we asked to the neural network. So, given the M right now, what is the most probable letter? And so the network is going to answer Y, okay. But so they've done like a very interesting analysis, okay. So like you have like this other neuron which activates after opening of a quote. Okay, so after the opening of this quote, it just activates, it goes red, and deactivates when the quote ends. Okay, so you have like kind of like specialized. So most of the time it's impossible to do, right? But like that's an example of neurons that are like responsible for long-range dependencies. Okay, so it's just like despite its form, right? It doesn't. It has like some memory. Okay. Okay, so now go back to with the experimental acquisition. So we can train it. We can train it live. Okay, and so so what we do in practice? So we input like the voltage one by one. Okay, so here I have unfolded the recurrent neural network, but we input the voltage step by step. Okay, and at each time it makes a prediction. But with getting the bit y that corresponds to the tomography, right? Given the voltage trace.
And the weights are uniform.
Yeah, the weight network is giving me like one prediction at every time point, right? But I'm only training it on the last point of the sequence. But I'm varying the length of the sequence in order to span the dynamic. So, but this is what I'm learning: the prediction of getting the outcome y.
But what is the training set? So you need to do this first on training set.
Yeah, so you know, I have like this, all these instances. So I have like many stochastic traces, like 1.5 million, right? I have like 1.5 million output bits, right? And so I give it this, and I see if and the loss function is comparing the prediction with the actual measurement, the projective measurement overall. So yeah. And so I can show those data in this like block sphere way. So you see, like with this 3 axis of tomography, I'm able to reconstruct the full state of the quantum system, right? I have like I fitted the free probability distribution with the recurrent neural network, and from that I know like the position of my qubit in the block sphere. Now I can look at the measurement back action. So what the variance of the flow, okay, in the block sphere, and you can see that if I'm here, there is very little noise because it corresponds to the pointer state, right? So I have like very little back action. But however, if I am on the equator, I'm very likely to be pushed up or down, right? And so from this, I can extract the measurement axis, okay, and the measurement strength. And like a nice quantity is also the quantum efficiency, which is like a factor of this dW term right here. So like by comparing like the dephasing rate and the measurement right here, it's still useful if you are like a slightly more complicated system, like let's say 2 qubits, a few qubits, right? Yeah, that's it. So I thank you for your attention, and so that's the team of Berkeley, and I've performed this experiment with Shea and Lee Martin. Thank you.